Hello everyone, this is Rashmi S, pursuing Integrated MSc at Physics course at Regional Institute of Education, Mysuru. Today we are going to discuss about a new topic called solid layers in smectics. Here we will be discussing about the introduction, structure, its types, phase transition, application, challenges, and importance of solid layers in smectics. Smectic liquid crystal is a type of a liquid crystal characterized by layered structure in which molecules are having certain degree of order and that can also exhibit the solid-like behavior unlike pneumatic liquid crystals. Where the molecules are generally aligned along a common direction, smectic have both orientational order and also a layer positional order. These layers are made up of the molecules arranged in ordered structure. The solid layers in smectic play a very crucial role in their unique properties and also its applications. Smectic liquid crystal is characterized by their unique layered structure where the molecules can exhibit both the orientational and transitional order. The molecules in solid layers of smectics are typically elongated and have a preferred orientation. Interaction between the molecules within the layers determine the layer spacing and the stability. There is also a molecular arrangement in smectic layers. Layered order. In smectic phases, molecules from distinct layers form a very regular spacing between them. Within each layer, molecules which can exhibit the different degrees of order depending upon the smectic phase. These layers can be visualized as a thin sheets stacked in a specific pattern where the distance between these remains relatively constant. Next, here it comes the orientation within the layers. In the smectic phases, molecules usually have a preferred orientation. They can be aligned parallel to each other with their long axes pointing in the same direction. However, the exact orientation relative to the layer plane can vary, leading to different subtypes of the smectic phases. Defects in the layer structure can influence the optical and the mechanical properties of the material. Layer spacing in smectics is typically measured using techniques like X-ray diffraction or small angle X-ray scattering, which is also commonly known as SAXX. These techniques allow researchers to determine the periodicity in the structure and calculate the distance between the layers with high precision. The spacing between solid layers in smectics is influenced by factors like temperature and molecular structure. Changes in layer spacing can lead to phase transition between different smectic phases. Control over layer spacing is important for tuning the material properties in various applications. Dynamics of the solid layers. Solid layers in smectics can exhibit dynamic behavior including layer rearrangements and fluctuations. The dynamics of the layers can affect the material's response to external stimuli also. Understanding the dynamics of the solid layers is very essential for designing the responsive material. Now we are discussing about the optical properties. The spacing can affect how the material interacts with light, influencing its refractive index and other optical characteristics. The organization of solid layers in smectics can give rise to unique optical phenomena like birefringence. Birefringence results from the anisotropic refractive indices of the material within the layers. The optical properties of the smectics can be tailored by controlling the orientation of the solid layers. Mechanical properties. Layer spacing impacts the flexibility and mechanical stability of smectic materials. Smaller spacing can lead to more rigid structures, while layer spacing may allow more flexibility. The solid layers in smectics contribute to materials' mechanical properties like elasticity and viscosity. The layer structure can influence materials' response to mechanical stress and deformation. Understanding relationship between solid layers and mechanical properties is crucial for applications in flexible electronics and coatings. Understanding and controlling layer spacing is crucial in designing smectic-based devices and materials for a wide range of applications, including liquid crystal displays, sensors, and other advanced materials. Next comes the solid-like behavior in smectics. Smectic liquid crystals are a fascinating state of matter because they exhibit properties of both liquids and also the solids. Sometimes it might be gas also. So this unique combination allows the smectic phases to demonstrate solid-like behavior under certain conditions, which has a very significant implications for their mechanical and also the physical properties. The solid layers in smectic can maintain their orientation and structure over long periods of time. This solid-like behavior is crucial for application where the stability and control are essential. Smectic phases can exhibit several types of solid-like behavior, including mechanical rigidity, reduced flow, and elasticity. Some of the examples of solid-like behavior in smectics are smectic B, smectic F, smectic I, and other complex smectic phases. Here comes some of the types in solid layers. Smectic phases can be classified into different types depending on arrangement and orientation of the molecules within and between layers. Some of the common types include smectic A, smectic B, and smectic C phases. First, let's talk about smectic A. In this phase, molecules are arranged perpendicular to the layer plane, leading to parallel stacking of the layers. This is considered as one of the simplest and most symmetric smectic phases. The molecules can move laterally within the layers but have limited movement between them. Next, there is smectic C phase. This phase is characterized by a tilt in the orientation of the molecules relative to the layer plate. This tilt creates a more complex structure and can lead to chiral properties if the tilt direction is consistent across the layers. Next, there is smectic B. In this phase, the molecules within each layer exhibits the crystalline order, forming a hexagonal lattice. This added level of positional order gives smectic B a more solid-like characteristics compared to the other smectic phases. Phase transition in smectics. Smectics can undergo phase transition between different layered structures like transition from a smectic liquid to smectic solid. These transitions are often driven by changes in temperature or pressure. Understanding the phase behavior of smectics is important for optimizing their properties for specific applications. Now let's see some of the application of the smectic solid layers. Smectic phase with their distinctive layered structure and unique combination of fluidity and rigidity offer a very wide range of applications in various fields. Their solid-like characteristics coupled with the ability to manipulate their orientation and alignment make them valuable in both traditional and emerging technologies. Here's a look at some common and emerging applications of smectic solid layers, like in LCDs and in optical devices because of their bifringence and ability to align in a specific direction make them very useful in applications like optical modulators, polarizers, filters, and optical filters. These applications of the smectic solid layers are very diverse, spanning technology, optics, sensors, smart materials, and even biochemical fields. A combination of the solid-like behavior, layered structure, and responsiveness to external stimuli makes the smectic phases a very powerful tool in a range of applications. Understanding their unique properties continues to open to new avenues for innovation and technology development. Control of solid layers in smectics. Researchers are exploring various methods to control and manipulate the solid layers in smectics. External fields such as electric or magnetic fields can be used to align the layers in a desired orientation. Surface treatment and additives can also influence the structure and the behavior of the smectic. Here come some of the challenges in studying solid layers in smectics. Studying solid layers in smectic liquid crystals presents a variety of challenges. These challenges stem from the complex nature of smectic phases, their transitional behavior, and a specific techniques required to examine them at a molecular level. Here are some of the key challenges in studying the solid layers in smectics. That is structural complexity, measurement techniques, dynamic behavior, interdisciplinary knowledge, and in real-world application challenges. Despite these challenges, the the study of the solid layers in smectics is a vibrant field with significant potential for innovation and technological advancement. Addressing these challenges requires a combination of advanced techniques, interdisciplinary collaboration, and ongoing research into the underlying principles governing smectic behavior. As researchers continue to overcome these hurdles, smectic phases may find broader application in variety of industries from consumer electronics to advanced material science. There are some of the future directions in smectic research. The future direction in smectic research is poised for exciting development as researchers explore new applications, uncover deeper theoretical understanding, and leverage advanced technologies. Ongoing research in smectics aim to uncover new properties and applications of solid layers. Advances in material science and technology may lead to novel smectic-based devices with enhanced performance. Collaboration in between scientists from different disciplines will be a key to unlocking the full potential of smectic solid layers. Here comes the importance of solid layers in smectics. Solid layers in smectics are a critical feature that distinguishes these phases from other types of liquid crystals, such as pneumatic or cholesterols. The presence of the solid-like layers in smectic phases is important for a variety of reasons, ranging from their fundamental properties to their broad applications in technology and material science. These solid layers in smectics are fundamental to unique properties and wide-ranging application of these liquid crystal phases. Their combination of structural order, mechanical resilience, optical versatility, and thermal stability makes them valuable in both established technologies like LCDs and emerging fields like smart materials and biomedical devices. Understanding and leveraging these solid layers is a key to advancing smectic research and unlocking new opportunities for innovation. Here is the conclusion of what we have discussed for so far. Thus, solid layers in smectic play a very critical role in determining the material's properties and its behavior. The organization, dynamics, and properties of the solid layers are a key considerations in the design of smectic materials. Continued research in solid layers in smectic holds a promise for a development of innovative technologies and also the materials. The conclusion on solid layers in smectics encompasses several important aspects such as structural distinctiveness, practical applications, and challenges in future directions. Solid layers in smectic play a central role in the behavior and application of smectic liquid crystals. Their unique combination of solid-like structure and liquid-like fluidity opens a range of possibilities in material physics. The ongoing study of smectics with a focus on their solid layers promises to yield new insights and applications, driving advancements in both established and emerging technologies. As researchers continue to explore the complexities of smectic phases, the potential for innovation in these fields remains strong, with the implication for various industries and also the scientific disciplines. So, this is the end of today's topic, solid layers in smectics. Thank you.